complex variable has the equation z bar minus 1 is 0. And as we all know, if we take non-negative polynomial on the circle, so if we take f let's denote by gamma, or t if you want the torus, then we know that f can be written as a single Hermitian square. This is the famous Ries-Feyer theorem, which is elementary. In this case, you can identify the roots and so on. And this is the root of a lot of important results. Jean-Bernard asked me to speak about the spectral theorem, and I'll show you soon how this implies the spectral theorem. So anyway, this is Ries-Feyer, 1913, and it's an extremely important result. To put it into the general context, I would like to denote by I the ideal of the principal ideal of the circle, and remark that this is a real ideal. It's invariant under conjugation, obviously. So this result is equivalent to the fact that f polynomial non-negative on the circle implies that f belongs to a Hermitian sum of squares modulo the ideal of the circle. Second example. This will be somehow the leading thread for us, very well understood.
Dimensional case, was it much later, or was it with positivity?
I'll explain the higher dimensionals in a second. Let's perturb a little the circle. Let's make it an ellipse. Very small perturbation. So let's look at the equation z bar plus a small alpha z square, z bar square minus 1 is 0. With alpha is real and very small. You can compute immediately in x and y coordinates, and you see that this is an ellipse. And I am asking the same question. So take a polynomial, let's denote this by e, the ellipse. Take a polynomial f, which is non-negative on the ellipse. What do you think? Is it true that can be written as a sum of Hermitian squares modulo the ideal of the ellipse? Yes or no? What do you think? Klaus is excluded from here because this is joint work with Klaus. I'll mention what we did and except Klaus. What do you think?
Maybe we can apply a transformation and make it into a circle, then it is.
Yes, conformal transformation, but will destroy the polynomial ring. You will end up with transcendental function. Or if you want the exterior of the ellipse, it goes by Joukowsky map, but then it's no more a polynomial. Okay. No, doesn't work. The transformation doesn't work. Yes or no? What do you think? No. So let me show you. If alpha is different than 0, let's take f a very special. Let's take a constant minus modulus of z square. Very basic. And let's assume that this is a sum of squares plus something in the ideal, something which is here, this ideal. Let's imagine the decomposition. Here we have a sum of Hermitian squares. And let's look at the leading term. The leading term here, the highest order term, contains z bar, is invariant, but also contains z square and z bar square separated. the leading term here contains z bar because it's polynomial only in z times its conjugate. So if we just chase the leading term, we'll remark that this is not possible. Very annoying. So if I deform a little the circle, the result is no more true.
It's like the torus is an accident.
We'll arrive at the torus in a second. That's the aim of my talk. Now, to go a little higher dimensions, let's look at the third example. I want to keep on the other blackboard the notation. So example number 3. Let's take the sphere, unit sphere in CD. Yeah, so this is the unit sphere in d-dimensional space with d bigger than 1. Same question. The ideal will be, of course, generated by the norm of z squared minus 1. And if I take a polynomial in z and z bar, which is strictly positive, in higher dimensions we have to go to strict positivity, then it follows that indeed it is a sum of Hermitian squares plus the ideal of the sphere. Who proved this? There are several authors. Quillen, 1967. Independently, Atavale, 1988, I think. Independently, Kathleen, D'Angelo, 1998. 3 independent proofs.
So
Hard.
why it took so long from the one-dimensional case? Because they were not interested or they could not prove it?
Well, the people were interested more in the torus, not on the sphere. So the bitorus, the n-dimensional polydisk, it was much more interesting. This was a rather peculiar work published in Invenciones by the early algebraist Quillen with analytic tools. So the interesting part is that all 3 authors proved this purely algebraic result with analytic tools. And this is the theme of my work, which I share with Klaus. And I'm trying to convince you that in these situations it's good to evaluate such decompositions not on points, but on matrices. And to go with what we call a quantization. That means we replace the variables by commuting matrices and we put certain conditions, and then they will better separate not only the points, but they will separate directions. We spoke about jets and so on, and along this theme, we can understand much better why this phenomenon holds. Now, I'll call such a condition Quillen's property, and this is the start of the theoretical part of my talk. I'll comment a little how they prove it, so independently the 3 of them. Okay, so with these preparations, let's do some general framework now.
For negative, this
Is not true. Example 4 z1 minus z2 square non-negative on the sphere S3, but it's not a Hermitian sum of squares. for the simple reason that they will be equal and they will stay on a torus embedded on this sphere, and torus is a uniqueness set for analytic functions. If this would be a sum of Hermitian squares, all summands would be 0 on that torus, and that implies that they are identical. So that's the simplest example, S3. Okay, so back to the general framework. I is an ideal, which I'll assume real. That means invariant under complex conjugation. And also I'll work with the zero set, the real zero set of the ideal. So these are the points Z in CD, so that F is in the ideal. And I'll assume for the talk today that this is compact.
This is Z in C to the D or R to the D?
R2D or CD. Yeah.
Why do you call it VR?
Because we work with real ideals, and we'll complexify in a moment. We'll go to the polarization, and then everything will become complex. So you will see in a moment. So I assume that this is a compact set. And now the conditions. When is happening that we have Quillen property, which was that if F is a polynomial on the variety, strictly positive implies that F belongs to Hermitian sums of squares modulo the ideal. The ideal may not be reduced. That's the interesting part here. We may have nilpotents. That's what we have seen, that it happens and not on several varieties. Well, we know now, after this week of refreshing our real algebra, we know that the Archimedean property is very much related to this. And this is simply to say that this convex cone is Archimedean. Which means simply that for a sufficiently large constant minus modulus of this square, this belongs to the ideal. Well, it is a general fact and not very well known. And here I start telling you about results which are in a series of papers with Klaus. If this convex set has the Archimedean property, then we have Quillen. Why? I can test your knowledge of real algebra. It's a little tricky because we use general positive Stellensatz. It's in the book of Prestel and Delzel, for instance. And we have to use the fact that this is a semi-ring. That means it's closed under addition and multiplication. And it has the Archimedean property. Remark that if we multiply elements here, we remain there. So this is due to general positive Stellensatz. However, this condition is hard to check. Going back to the sphere, we see immediately that this provides a quick proof of Quillen's theorem, because the equation of the sphere is of this form. How do we check this condition? And the next step is, as I mentioned, quantization. Let's try to evaluate the polynomials not on points but on matrices, or operators even. So let's take a tuple of commuting operators bounded, which satisfies the equations embedded in the ideal. I'll simply say that T is perpendicular to the ideal, meaning that when I perform the substitution of the variables by T and T star, this is 0 for every f in the ideal. Very important observation here. T doesn't commute with T star, so I put all the stars to the left of the powers of T. So you imagine monomials here, and I make a choice to put all the stars to the left. So the condition is, if I have such a commuting tuple and I evaluate elements of the algebra on it, this will imply that T is subnormal. That means I can put T in a larger block matrix of D commuting operators, which is normal. We call this subnormality, and I'll explain why. This looks very artificial, but I'll show you examples that this is rather natural. Then, a relaxation of this condition, which is obviously true, finite rank such commuting. So let's not work on an arbitrary Hilbert space, but of finite rank. So same, but the rank of each entry is finite. And again, the condition will be subnormality in finite rank means simply that T is normal. This looks hard to check. However, the last condition is equivalent to a very beautiful set of geometric conditions. So far, I didn't enter into the geometry of the situation, and I didn't explain you why the disk is different from the ellipse. And here it is. I'll call this the diamond condition. And to state it briefly is the following. The ideal I, unfortunately I have to use a negation here, is not contained in any ideals of the following form. For two distinct points, this the ideal of polynomials which vanish at the real points, but when I polarize also at the mixed ones, for alpha different than beta. I'll make a picture in a moment. Or an ideal associated to a single point alpha and a Hermitian matrix, D by D matrix, which is a little more involved. So polynomials f with the condition that they are 0 there, and then the matrix annihilates is a kind of jet condition. The z bar equation at the point alpha, and also the Levy form, the Hessian, complex Hessian, at the same point alpha. Well, this is the hard part. And I wanted to arrive here just to tell you, I'll make pictures in a moment, that there is a string of implications At the end of my talk, I'll give you examples showing that each of them is strict, except this one, leading to a very geometric understanding. So let's make some pictures. This is in a recent archive note I put with Klaus on the net and on the web, and you can find the full proof. And the idea is very simple. Let me explain this one. Why having 2 points on the variety alpha and beta with this property will prevent having equivalence property. That's the major idea. So let's make a picture. Suppose that we have the variety, and we have this is the real variety. We have such pair of points, and now imagine that we embed diagonally CD into the Cartesian product. And then from the diagonal we extend to the variables, we free the z bar. This is called polarization, and it's very useful because for analytic functions, for all our purposes, this operation is unique. We lose nothing. So suppose that we have these points, and then when we extend and we polarize in the bigger space, we have also these points. So this is alpha beta bar and beta alpha. Condition D means the following, that if we have a pair of points on the variety, so that when we polarize, automatically the extension of this ideal, by the way, the extension will be, the polarized ideal will be the tensor product with 1 plus 1, the conjugation. It vanishes at this point, then we prevent equivalence property. Why it is so? Suppose that every strictly positive polynomial f belongs to Hermitian sums of squares modulo the ideal. Let's look at this pair, alpha and beta. What it is so special about Hermitian squares? Let's take one of them. If I take age, Hermitian square will be, let's say, age alpha and age beta bar. It satisfies the Cauchy-Schwarz inequality. Very basic. So this is less than age alpha. Obvious in this case, but even if you take sums, if you take an inner product here, let's say we take an inner product, this will be normal for age. If we take sums, it's the same thing. So if these are 0, automatically this is 0. Therefore, if I look at this pair of points, f will inherit from the Hermitian sums of squares the Cauchy-Schwarz inequality. So f automatically will vanish at the opposite points. I assume that the ideal has this property. So automatically f, the whole polynomial will satisfy this vanishing condition. If it is 0 here, automatically will be 0 there. Not true. There are positive polynomials which can distinguish this point. So that's essentially the proof that non-D implies non-Q. Very geometric. Now, what is interesting is that if we put this at work, we have a lot of examples. So this is
trick to go to the operator T is just to prove these equivalences, SFD, because you didn't use this in the argument, right?
what argument?
To prove this at the end, you didn't use
No,
the intermediate step.
no. This is only if you want an explanation. The proof is much more involved, and this equivalence between
But you
the
only use only D, right?
Hmm?
You use only D, and then to get D, you have to go through those steps, right?
I can go directly, but the difficult part, and this is technical and I'll not touch it, is to prove that this finite rank normality is equivalent to a set of geometric conditions. So if you want, the problem is the following: given an ideal, and knowing that automatically any system of matrices satisfying the equations of the ideal is normal, is equivalent to a complete geometric characterization of the idea. That's quite interesting. And as I mentioned at the beginning, it's a big advantage, and that should be a leitmotif for my talk, that we go beyond point evaluations. We evaluate on matrices. So anyway, let's put this at work. Example, I think 5. 2D, z1 squared minus 1 divided by plus z2 squared, small epsilon times z1 less than 1 is a very roundish surface, is strictly pseudo-convex, which means by biholomorphic transformations is equivalent convex locally. It is algebraic, it is smooth, and does not satisfy Quillen's property. This answers a question which was raised more than 10 years ago by...
So what is the idea?
Hmm?
What is the idea here?
The idea is to find 2 points which make this ideal, this containment possible. And the 2 points are, let's see, 1, 1, and minus 1. So these 2 points will satisfy the inclusion. I will be contained in this ideal, and we prove that.
Okay.
So,
should it be equal one?
Hmm?
You put an inequality.
This is the boundary, yeah. When you speak about these bodies, you can sometimes include the interior. So this answers a question of Kathleen D'Angelo, which was open for quite a long time and of interest, essentially asking, is the sphere so special for this phenomenon discovered by Quillen? And the answer is there are other strictly pseudo-convex domains on which Quillen's property doesn't hold. Now, all this being said, as I mentioned, there are more interesting examples. Let me show you a little how Q implies S, because Jean-Bernard asked me to comment about the spectral theorem. First, let's go back to example 1. And let's understand on the circle why Q implies S. The equation of the circle is this one. Let's quantize it. Let's take an operator T which satisfies this what does it mean? T is an isometry, if you remember. It preserves angles and distances. It's a linear transformation. And there is a well-known fact that any isometry can be extended to a complete unitary transformation. You can put this T in a bigger matrix, which is unitary. And this explains why T is subnormal in this example. What about in general? So let's take Q and try to prove this. I have the ideal, and I have the assumption that every positive polynomial is there. Let's take T, a tuple of commuting operators, which satisfies the equations of the ideal, like in my example. Then the functional calculus I just mentioned, so we replace variables by T, will have the following property that when I write this, due to my assumption that I put all the adjoints to the left, this will be a sum of the form hk star hk of T. Finite. Because the ideal annihilates the tuple, doesn't appear here. But wait a minute, each of it, if of these terms, is a non-negative operator. So this is non-negative. So, big thing, if f is positive on the variety, this is non-negative. The transformation is linear. And now you remember a little measure theory that if you have such a map which takes positive polynomials on a compact set into some operation which is positive, is linear and positive, it is representable by a measure. So this will be the integral on the variety of f against a measure, positive measure, which depends on the point x. In fact, it's quadratic in the point x. Well, guess what? This can be lifted to a spectral measure. So this is a general fact proved by Naimark 1943. Any such vector-valued, operator-valued positive measure can be lifted to a bigger Hilbert space, to a spectral measure. That means there exists a normal operator, possibly on a bigger Hilbert space, which satisfies the same equation. And this is almost a tautology these days. The Naimark dilation theorem is very simple. It's something you should not be afraid of if you hear about it. But I can polarize. I can take instead of x, 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 y. And I'll have simply the fact from here, it's immediate that T can be embedded into a normal tuple of operators exactly with a 0 here on an invariant subspace. So that's the whole proof. Very, very simple and very illustrative for how the spectral theorem comes into play here. So this is more or less the string of conditions. Now, what they are good for. And I'll turn the page and try to show you how we can work at this level, at condition D, to distinguish between ideals and to introduce an invariant which is very useful for the geometry of real varieties in complex space. Yes.
Something about the finite rank condition.
Which one?
From S to SF.
So from S to SF is almost nothing, because if you have a finite rank tuple,
Or if you have it, you're not guaranteeing that
yeah.
you'll get finite.
So you assume that if it is finite rank and satisfies the same condition, then it is normal. That's
I see, but it's
that's
not,
immediate.
it's not true in general that this will.
No,
Yeah.
of course not.
Right, right.
I'll give you an example.
Yeah, that's fine.
They are not equivalent,
Right.
and it's not totally trivial. So let's turn the page. All this is fine. I'll use this part of the blackboard for the rest of the definition. And this is joint work with John D'Angelo, which complements the work I mentioned. So we have such an ideal. And I'll speak about the Hermitian complexity of the ideal to be the cardinality of these points. I'll denote them now alpha and alpha bar. So that I, so maybe I should put like this, is contained in all these ideals. It is a little more complicated because you can have multiple points, so and then you have to speak about ideals of finite codimension. I'll not enter into details. So this multiplicity can be taught as single point with multiplicities. But anyway, it's a well-defined concept. This is the Hermitian complexity. Of course, 1 means that we have only one point and there is nothing to say here. Here, essentially, we have 2. And 1 is trivially 2. It can be infinity if this cardinality is not finite. So this gives an invariant up to
This is meant for all I, j.
for all
Was it?
I and j. How do we compute this? Let me give you a whole list of examples which will clarify why the sphere is so special. Example 7. Let's take one single generator, R, of the ideal, a hypersurface in CD, and this is Hermitian, so always we can write this as sum of Hermitian squares. I'll write it in short like this, vector valued P, minus another sum of Hermitian squares. And we can use this minimal, this representation, so that we don't have redundant terms. Okay, and I'm looking at the ideal generated by R. Like the sphere. The sphere will be 1 minus modulus of z squared. I would like to compute the Hermitian complexity. So here is a simple fact of this ideal. This is the maximum of the multiplicity of the map P minus U where U is an isometry from the space of Q's into the space of P's. So you run over all rotations, and you are looking at the map now, P minus U Q, between, let's say, CD, CM and Cn. This is a polynomial map. If it is finite, it has a certain multiplicity, the number of points in the fiber. This is what I mean here. If it is not finite, this is infinite. And the fact, which is rather easy, and you can take it as an example, the Hermitian complexity of the hypersurface given by this equation is exactly equal to this number. So it is reduced to an algebraic multiplicity. And this is, as you know, generic. You can compute points in fiber count, pre-images, and so on. More interesting is that in the same situation, this is infinity if and only if the variety contains an analytic disk. A complex analytic disk. So you can put on this hypersurface, which was like the sphere or the torus and so on, you can put an analytic disk. And this characterizes infinite Hermitian complexity. So what we are doing here is essentially we have a stratification of the condition D with all these numbers, the Hermitian complexity, and this gives a better understanding why Quillen phenomenon fails. Hermitian complexity 2 is the weakest failure, and Hermitian complexity infinity is the strongest failure. A simple exercise for you: suppose that on the variety you have an analytic disk, you have such a leaf. Prove that you cannot have condition Q. Not every positive polynomial, if you have a complex leaf, can be written as a sum of Hermitian squares. Little exercise. Yes?
I have a question about this, the Quillen property, because normally you could have the property A by replacing the sum of Hermitian square by the classical sum of square, right?
I'll comment this. Then everything is different.
Yes, but the idea of Quillen was to specialize even more.
To specialize to Hermitian squares, and is very important for applications, for instance, to this evaluation on matrices. And in the last 15 minutes, I'll turn the page and go from varieties to semi-algebraic sets, and it will become even more clear.
So Mihai, does this disk contain these points from D? So these alpha I, alpha j that you have?
You have infinitely many.
Many.
You have a
So
lot.
they're from
Yeah,
there.
you have a lot of them. So, simple exercise. Suppose that you have such an analytic disk. Yeah, it's hard to figure. Suppose that you have such a complex analytic variety contained on your variety. Why a strictly positive polynomial is not a sum of squares? That's something to think after we finish, or while we are still continuing. So that's the picture in any number of dimensions. Before we finish, I want to show you one single example that S is not equivalent to itself. By the way, the ellipse shows that this is not true, just looking at the ellipse. nice little discovery that the ellipse doesn't have a Swiss-Equilibrium property, but any operator equation mimicking the ellipse leads to a subnormal tuple. While this is not true, this is the next example.
Again, why is it not true? For the ellipse, it would be true if you use sum of square.
Sure. Yeah.
So why is it so worried about that?
Why I'm so worried? Because I want to use this matrix evaluations. I want to do operator theory on the ellipse. And then I'll show you in a minute that you don't have, for Neumann inequality and other fine things, you don't have a good spectral analysis on the ellipse, in short. Let's take the circle with a double point here. So I take the equation of the circle, let me write it in real coordinates, and then I have to add to this the equation of the point here, which is x minus 1 plus y, for instance. Yeah, I add to this. There are different ways to write, for instance. I put more weight on the point. Well, there is an operator, namely this one and the one here, infinite, which satisfies this equation of the circle with a double point, so annihilates this ideal, but it is not subnormal. On the other hand, any finite rank matrix which satisfies these equations, the circle plus the point, is normal. So that's why they are not equivalent. Okay, the last 10 minutes about semi-algebraic sets. So we have all these conditions. And now, as we have seen this last week, let's work not with an ideal, but with a quadratic module. But I'll take a quadratic module over the Hermitian sums of squares. This is back to the work with Klaus. We have the positivity set of this. These are the points Z. And we can ask the same questions. Equivalence property, Archimedeanity, subnormality, and so on. What remains? Very unexpected and interesting, Archimedeanity will not imply equivalence property in this case. Why? Because although this is a module over the Hermitian sums of squares, this is not an Archimedean semi-ring. So be careful when you use the general positive Stellensatz, you need the Archimedeanity of the semi-ring, which is behind the module. Otherwise, it is not true. So in this situation, simple examples show that this is not true. But quite interesting, the subnormality is equivalent to S if this set is what we call polynomially convex. Doesn't have holes. We can separate points from the set by polynomial inequalities. So the situation is quite parallel, and I'll finish to be in time with the last example, which is the most illustrating for us. Rather than the torus, I'll take the disk. And you will say, what a big deal to pass from the circle to the disk. Well, it is. And of course, the equation is now this one. So the quadratic module will be given by the Hermitian sums of squares this way. And we can immediately see that there are positive polynomials which do not belong here. So simple observation, there exists f strictly positive on the disk, which is not there. Try to find one. What I want to show you is that this is a very well-known convex cone in operator theory when we apply this to operators, and it leads to highly non-trivial results. And this will answer also some Jean-Bernard questions. And here is the fact. If I don't take all polynomials, but I take only the harmonic ones, this remains true. So take now age an analytic polynomial in one variable and assume that the real part of age is non-negative on the disk. I claim that then this is in the module.
Yeah.
Yes.
When this property is true, is it the same as saying that the associated moment problem is just that you look at the moment with z to the power k and not z bar or products?
No, it's more complicated because you have you mix z and z bar, but you don't take powers of polynomials and z bar to. There is a moment problem here behind. You don't take all possible powers. You take only, when you take g of z modulus square, it is quite different than taking f of z and z bar modulus square, even if the degree in z bar is 1. And there is a moment problem. I'll arrive at very soon to it. So, to finish, why this is so? Let me give you one answer and then the non-trivial implications, and I'll leave on this tone. We know that on the boundary, so we are on the disk. We know that on the boundary, this is a square. So let's write it. So e to the right is a square, let's say q. Fair is old and tired result. But this is harmonic. How do we produce a harmonic polynomial from the boundary? Poisson's formula. Therefore, the real part of h of z is, if you remember the Poisson integral from complex variables. This is 1 minus z squared, e to the I theta minus z squared. And here I have q. And I'll do the following. I add and subtract q of z. Very simple computation. I break this square into this square plus this square and the mixed terms. When I write this square, so maybe I'll write it here. I'll have 1 minus modulus of z square q and the free term. This doesn't involve the argument of integration, so it comes out, so this will be q of z. Because the terms, the mixed terms are harmonic, the result of applying the Poisson transform is replacing e to the I theta by z, so they become 0. There is nothing else. Now, this one is a sum of squares, because this is a polynomial in e to the I theta and z. When I integrate on the torus, you have the nice cancellations, and this will be a sum of Hermitian squares. So, in short, we have the proof of this fact. Very classical. Why it is good for, and I'll finish here. So, for the theory of this quadratic modulo of a Hermitian square, why it is good for. Let's play the same game, quantization. Let's take an operator which satisfies the equation of the disk. That means t star t is less than the identity. And let's remark that according to my fact, the real part of h of t is non-negative. Well, this is a highly non-trivial fact. This is called von Neumann's inequality. Was proven in 1953, towards the end of his short life, by von Neumann, and this is the beginning of a whole story in operator theory. This inequality, even for 2 by 2 matrices, if you want to see it at work, take a 2 by 2 matrix which is contractive, take an arbitrary harmonic polynomial at your choice, and see that the bounds of the harmonic polynomial are preserved by applying the matrices. That's called von Neumann. And we do the same game as before. Because this is non-negative, it's a linear transformation, depends only on the function restricted to the boundary, will be the integral on the boundary of some operator valued measure, which by Neymar can be taken to be a spectral measure. That means orthogonal projections. But that means that this is the real part of h of a unitary transformation applied to the respective vectors. This has the name of Sekeval-Vinag dilation theorem, and shows that any operator like this, believe it or not, can be inserted into a unitary which looks like this. all the powers restricted to the vectors of the original space will remain intact. But you cannot mix, as before, adjoints and the operator. And this has far-reaching consequences. It is much stronger than the spectral theorem for unitaries because it applies to all contractive transformations, as you probably know. So, in short, this is the story. What I wanted to tell you, and the conclusion, there is an advantage working with Hermitian squares because the representation of the quadratic form is unique. You don't have the ambiguity which you encounter over the reals, which gives you the polarization for free. So you can, essentially you can free Z bar from Z in all computations, and you can go in the whole space. And then second, once you do this, you can replace variables by matrices, by operators, and this gives you an insight even into purely algebraic statements. You see, this is a very algebraic statement, and going it via matrices, you arrive at a geometric understanding of it with all the consequences I mentioned. The quadratic module situation is also very interesting. I didn't say much, but there is a parallel. This is an example which is very dear to operator theorists, and it goes into higher dimensions, but with some additional restrictions. So I'll stop here. Thank you very much.
Well, any question?
Yes.
So if you're, as far as I understood, if you're not interested in sums of Hermitian squares, but just in sums of squares, like up there,
Yes.
then it's just the usual theory.
It's the usual theory, and there is not much to say.
So say you don't like these complex numbers and conjugation stuff.
Yes.
Can you formulate these questions? Can you formulate these questions in a purely real setting somehow?
Yes, but then you replace them by 2x2 matrices. Yeah, you can go into the representation of the complex as 2x2 matrices, and I think you can do it. I was accused by my colleagues in Santa Barbara that I am too complex and too linear, because they are real and non-linear. So I remain faithful to complex and linear. Yeah, I think you can do it, but then you accept the matrix representation.
Well, thank you very much.